yesterday I gave you, we introduced this little formula. And A is equal to P times 1 plus R over N to the NT. And the homework I gave you basically was a whole lot of repetitive use of this formula. Like if you did your whole homework assignment, you know this formula backwards and forwards. Like you know this so well that if I just wrote something down, you can tell me everything about the problem, right? If I just write this down, how much money did you start with? 2,500. What was the interest rate? 3. All right. How many times are you compounding?
Monthly.
Monthly, 12 times a year. And how long are we doing it?
5 years.
5 years. See, if you've done your homework, you can just look at that and pick all those numbers out, right? So now, why did I want you to practice that? Well, we're going to learn something new today, right? First, and this is my story for it. So a bank is offering a special promotion. They are going to offer 100% interest rate, right? But there's some restrictions, right? The restrictions are you can only invest $1 and you can only keep it in for 1 year. So then the question is, how much money can you make? Okay, all right. So let's say this. So if you invest $1 and you get 100%, how much money do you have at the end, after the end of the first year? You have $1 extra. Are we okay with that? Because 100% says you're doubling your money. Well, that's if you compound once per year, right? Because what you're assuming, right, is remember yesterday we were talking about you can compound multiple times a year? Well, if you compound once a year, it's like you have $1, and then at the very end of the year, you get 100% of that added, so that's where you get the $2. So if we start with, we compound once, we get $2. What does this look like if we compound twice a year? Like if we compound twice a year, then we start with $1, it's 1 plus, the 100% is 1, but if we compound twice a year, we get that. Everybody see that? That's your interest rate, which is 1, but we're compounding twice a year, so we get a 2 here and a 2 here. And so when you type that in your calculator, what do you get? What do we get? You get $2.25. Ah, more money. I said $2.25. Why not write a 4, right? So remember yesterday, the more times you compound, the more money you get, right? So if we compound twice, hey, we're at $2.25. Well, what if we compound monthly? What if we compound 12 times? What do we get? Type in. Here, I guess I'll type 2.
It's something wrong.
I don't think that it's supposed to be it's supposed to be kind of close to the $2 mark, right? So if we do 1, and we do, what's that? 1 plus 1 divided by 12 to the 12th, 12, not 2. No, $2.61. We're getting more money, right? Now, obviously we're not going to get an infinite amount of money, but I'm curious if we get to $3. Right? So the more times you compound, right, you get there. So what's next? What should I try? 240. I like that daily thing, right? So try 240. Of course, now you can just sort of scroll over. And I'm going to cheat a little bit, right? So if I go to 240, all right, that's fine. So 240. $2.71. We're getting more. I don't know if we're going to get $3, but we're getting more, right? Well, what would be a crazy number of times to compound?
10,000.
What?
10,000.
10. Why stop there? What about 1,000,000? I mean, your calculator's doing it, right? Why do you care? Let's see what happens if we do 1,000,000. And it's not too bad, right? We can go over, like we just basically change this number to 1,000,000. So 1 with 2, 3, 4, 5, 6. And then go back over here. And then 1, 2, 3, 4, 5, 6. And press enter and I don't think we're going to hit $3, are we? We're kind of $2.71, $2.71. You know, I want to do one more time, right? I want to compound it 1,000,000,000 times. Basically add on 3 more zeros, right? So if I add 3 more zeros, I can just go over here and put 1, 2, 3. Go over here. Wow, that's a lot of zeros. 1, 2, 3. Enter. Yeah. It's like we're going out, right? Like the difference between compounding 1,000,000 times and 1,000,000,000 times, all of these are the same. Doesn't start changing here, right? But, well, that number is kind of interesting. Like we're approaching something, right? Can you see the more times I compound, it's like I'm approaching something. It's less than 3, and it looks like it's approaching this number 2.71828, yeah, something. You know, I wonder where I've seen that number before. Sorry for those of you at home. What?
Is that what the E is on here?
Yes.
And then the E and the N, whatever. Like when we were doing dogs.
Yeah, that's that E, yeah.
Oh God.
Sorry, I have to wait all year to set this up, right? Because how long has that been up there?
Oh,
And last year and the year before, right? Yeah. So for those of you that have not been to my classroom, in the back of the room I have I have a little long strip that's a poster of digits of pi. It's got 75 digits of pi. In the side of my classroom I have something that says E equals, and it's this number, 2.71828, right? Turns out that's a special number that comes up in math. It actually comes up in math whenever you're dealing with logarithms and exponential stuff. Like pi shows up when you're dealing with circles, right? I shows up when you're dealing with square roots. And we are now introducing a new math constant, and it is this number E. Some people call it short for Euler's number. Euler is the, I know you think it's spelled with an O, but it's pronounced, the guy's Swiss mathematician Euler. He wrote a lot of stuff, and that's an understatement. If you stacked up everything that he wrote, let's say it's a pile this high, right? The second most prolific mathematician in history probably has a stack about half that high. So when I say he wrote a lot, that's an understatement, right? He wrote so much stuff that whatever notation he used, that's what we currently use. That's just because he wrote so much stuff around. If you're curious, he was the first person to call I the square root of -1. And because he used it, we still use it now. Before Euler, sometimes people would write the letters pi, and sometimes people would write the symbol pi. But after Euler, everybody writes this symbol. And Euler was playing around with this, and so he decided to call the number E. Sometimes they call it Euler's number. I don't think he would have called it after himself. He's not that much of an he didn't have that big of an ego. But these are your 3 math constants. And you've seen these before, and this is the first time you've seen this. So what is E? It's a number. It's less than 3. It's 2.71828. It goes on forever. It doesn't repeat. It doesn't end. Similar to pi. Okay? And I needed to introduce that. And this was kind of my fun part today. I like because I have this poster up. I had students made this for me a long time ago. And I like having it on the board because, first of all, in the beginning class, did y'all ever notice this? Did you wonder why it was there? For today. Pretty much I leave the poster up the entire year for today, and that's about it. Right? But, you know, what is E? you know, it's, yeah. There's other definitions of E. This is the one I like to teach with. All right, so are we okay with E? It's just this new number. There are some interesting things with it. As far as mildly interesting things with E, you have, if I said log x, what's the base of this? 10. Remember, every log has a base, right? And if there's no base given, you assume it's base 10, right? Well, it turns out log base E is going to be real important very shortly, right? And instead of writing log base E, we write this as, they write it lnx. Okay? Now, it's actually pronounced natural log. All right? So when you see this, this is natural log. And remember, like this was log base 10, and we know that log x and 10 to the x are related. Remember, because this was base 10 and 10 to the x. And if you look on your calculator, if you look at the log button, right above it you see the 10 to the x. Does everybody see that in their calculator? Well, right below the log button, what do you see? You see the natural log button. Everybody see the natural log? And what's right above that? E to the x, because they're related. All right, now I'm going to press pause just for a second because I don't want to. All right. So, all right. So this is that. So whenever you see natural log, that's just log base E. Right? And we're going to do some stuff with that very shortly. Right? But I like talking about the definition of E after we talk about that formula for compounding interest, so that we can, now we can actually define what E is. All right, now what are we going to do the rest of the day? Well, the rest of the day, we need to solve equations. And I don't have enough time to actually do this time. So, all right, so if I gave you, if I say 2 to the x is equal to 8, can we solve this equation? How do we solve it? Make the bases the same, right? You look at this and say, well, this is easy. All right, well, fine. This is going to be 2 to the x is equal to cubed, x equals 3, right? Easy, because we can make the bases the same. But what if I gave you 2 to the x is equal to 7? How do you solve that? Can you make the bases the same? No, right? So what do you do? And that's basically what we're going to talk about today. How do you solve an equation where you can't make the bases the same? Well, so we're going to start. I'm going to start with this one idea. Everybody ready for this one idea? You can't handle a variable in the exponent. Can we start with that idea? Everything that I'm about to teach hinges on the fact that you can't handle a variable in the exponent. Well, that's a problem, right? Because guess what we have? I have a variable in the exponent. So then how do you deal with that, right? How do you deal with a variable in the exponent? And we figure out a way to move it, right? We have to get the variable out of the exponent. Well, how do you do that? Do you remember properties of logs? If you had a log in front, what can you do with an exponent? Bring it down in front. And so what we're going to do is we're going to take log of both sides. You can do that. It's effectively, when you're solving equations, you take the square root of both sides. That's what we're doing. We're taking log of both sides. So has everybody written this down? All right. And now that we take log of both sides, what can I do with my exponent? I can bring it down front. That's what we did. And so now this is x log 2 equals log 7. All right. So here's what I want you to do with your calculator, right? I want everyone to type log 7 in your calculator. It's real hard. I mean, it's the hardest thing I've ever asked you to do. All right? You press the log button, and then you press 7. You don't even have to close the parentheses and press enter. And it computes log of 7. All right, and I'm gonna make another, incredible observation. That's a number. Whoa. Is everybody okay that's a number? Wait, we go one step further. You know what happens if you take log of 2 in your calculator? You know what you get? You get a number. Right? I know, earth-shattering, isn't it? I mean, this is honors, right? I've got to make sure we do difficult stuff, right? So, now, if I give you x times a number is equal to a number, how do you solve for x? You divide by 3, right? Is everybody okay with that? So if I give you x times a number equals a number, guess what you do to solve for x? You divide by the number. And so when I divide by the number, I'm going to divide by log 2, I'm going to divide by log 2. That's my answer. And it's okay for an answer to look like that. But, since we've got a calculator, I should probably show you how to type it in, right? So, how do you type log 7 divided by log 2? Well, let's get a fraction. So if you hit the alpha key and y equals, it brings up where you can have a fraction. And then you type in log 7 divided by log 3, and you press int.
It's log 2.
Oh, thank you. Log 2, and then you press enter, and we get our answer. Does everybody see how that worked? Right? So let's just sort of recap what we did. You got an exponential equation, but we couldn't get the same bases. So our first basic premise is we can't handle variables in the exponent. How do you get a variable out of the exponent? Well, you take log of both sides. That lets you bring the exponent down, and then you have to realize log 7 is a number, log 2 is a number. So I'll divide those, and then we type it in your calculator, and you get your answer. Does that make sense? Yes.
What decimal point do we go to?
Depends. Some problems I give you, they say they want 2 decimal places. Some say they want 3. Some say they want 4. I don't know what Alex wants. I'm thinking 3, but I'm not sure. Right? And actually, some answers they actually want your answer like this. Yes?
And we're allowed to round in these? Because I know the compound interest ones we weren't.
Yes, they didn't want you to round until the very end. There's actually Alex questions where they give you something like this, and they say, I want the answer in terms of log-based log. So this is the answer they want. All right, so your turn. Let's ramp up the difficulty just a little bit. Let's say I give you 3 to the 4x minus 2 is equal to 5. So we take log of both sides. Now what does that let me do? Bring the exponent down in front. That's the whole point of having that log there, so I can bring the exponent down in front. That's going to give me 4x minus 2. Make sure you put that 4x minus 2 in parentheses. And then I get log 3 is equal to log 5. So far, so good? All right, now, your job is to get the x by itself. What do you do first? We're going to divide by log 3. So I get that 4x minus 2 is equal to log 5 over log 3. Now what? Ignore this. Get the x by itself. What do you do? Add 2. So that's going to give me 4x is equal to whatever this is. Right? And then what's our final step? Divide by 4. Is everybody okay with that? So, let's see what that looks like when we type it in our calculator. I guess I should. So, let's see, I probably want a fraction, so I hit alpha, y equals. What? There we go. Oh, I need another fraction, so hit alpha y equals, there's another fraction. So I'm going to hit log 5 over log 3 off to the right plus 2, and all of that over 4. Isn't that nice how the calculator makes it look just like what it's supposed to? Yeah. And you press enter and whatever ugly number. Does that make sense? All right. Well, all right, we kind of okay with this? Well, what if I gave you 3 times 2 to the x minus 1 is equal to 5? What do you do now? Actually, what do you do first? Divide by 3. I want to make sure everybody understands, do you understand that taking log of both sides doesn't help? Because if you put a log here, you can't put the exponent down in front because of that 5, that 3's in the way. So we're going to divide everything by 3 first. That's going to give me 2. The x minus 1 is equal to 5 over 3. Now, what do we do? Take log of both sides. So I'll give you a few minutes to finish that. We have it? Well, okay. Well, what are we doing first? Take log of both sides. So we take log of both sides. So I can bring my exponent down. So that's going to give me x minus 1 and times log of 2 is equal to log of 5 over 3. Okay. Now what? Divide by log of 2 of both sides. So if I divide by log 2, divide by log 2, the x minus 1 is equal to that big old mess, which is log of 5 over 3 divided by log of 2, and then add 1. So I'm going to cheat a little bit and go ahead and put a plus 1, and here's our answer, right? And I was actually kind of excited in Alex. They actually have questions where they give you something that looks like this, and they say they don't want a decimal answer, they actually want an answer with this. And I guess you get really good with using the fraction button, the fraction tool on that. But let's see what happens. So it looks like I want to make a fraction, so I hit alpha of y equals, and this is going to give me log of 5 divided by 3, and I'm going to divide it by log of 2. Make sure I'm off to the side and hit plus 1. Is everybody okay with this? All right, how do we feel about this level of difficulty as far as exponential functions? Are we okay with this? All right. So, the basic idea is, like, everything starts on the premise that you can't handle a variable in the exponent. All right? So, when you see a variable in the exponent, you're like, well, okay, let's take log of both sides, and that lets us bring the whatever mess we have in the exponent, pull it down front. And I'm going to need to minimize this because I need more board space. But what if I gave you 3 to the x plus 2 is equal to 4 to the x minus 5? So what's different about that?
There's exponents on both sides.
You got x's on both sides. Well, I don't know how that's going to happen. I don't know how we're going to deal with that. But what are you going to do first? Take log of both sides, right? You can't handle a variable in the exponent, right? All right. As long as we know that you can't handle a variable in the exponent, we're going to take log of both sides, and so fine, we get log of both sides. Everybody okay with that? And the reason we took log of both sides is what's our next step? Put the exponents down front, right? And so that's going to give us x plus 2 times log of 3 is equal to x minus 5 times log of 4. Does that part make sense? Have I lost anybody? All right, we're all good? All right, now we're going to pause for just a little bit, and we're going to go over here. We're going to do an Algebra 1 problem, because I want to make sure that our Algebra 1 skills are where they need to be. Got it? Here's the Algebra 1 problem. You may want to write this out. Go off to the side somewhere, right? Flip over to a new page, whatever. This is scratch work, but it's an Algebra 1 problem. And my Algebra 1 problem is going to be x plus 2 times 3 is equal to x minus 5 times 4. First, can we agree this is an Algebra 1 problem? I know Dr. McCoy may have made you do worse than this, but can we agree this is an Algebra 1 problem? So if we put our Algebra 1 hats back on and we look at this, how do you solve this? What do you do first? You distribute. Okay, so I'm going to distribute. So I'm going to say this is 3x plus 2 times 3. I know it's 2 times 3, but you know what? I'm crazy, right? Because I think we have to establish that no sane person would ever choose to teach high school math. All right? If we can just start there, right? And so I'm just going to say it's 2 times 3. I know it's 6, but I'm going to say it's 2 times 3. And the same thing's going to happen over here. I'm going to say this is 4x. And again, I'm going to say this is 5 times 4. All right? Now, we still have our Algebra 1 hats on. What do you do next? You got x's on both sides. What do you do? Get them on one side, right? Are we okay? We're going to subtract 3x from both sides? Is everybody okay with that? So if we're going to subtract 3x from both sides, okay, so I do minus 3x. So I still have that 2 times 3 because I'm crazy. And yeah, I know 4x minus 3x is 1x. I know that, right? But I'm crazy. So I'm going to write it down as 4x minus 3x. I know it's 1x. I know. Now what would you do? Algebra 1 hats are still on. What would you do? Add the 20 to both sides, right? Right, I know it's 20, right? Wouldn't you just take that and put the 20 over here? So if I add the 5 times 4, and I add the 5 times 4, I get this 4x minus 3x, and on this side I get this 2 times 3 plus 5 times 4. Yeah, I know it's 26, but I'm crazy. And now I look at this. What's in common? Are we okay? There's an x in common? And so if there's an x in common, I pull the x out, and that's going to give me a 4 minus 3. And on this side, that gives me a 2 times 3 plus 5 times 4. And You know, now when I look at this, can we agree that this is a number? Can everybody agree that's a number? Number happens to be 26, but it's a number, isn't it? Can we agree that 4 minus 3 is a number? And there's an x. How would I get x by itself? Divide by the 1, right? And so then I end up with x is equal to 2 times 3 plus 5 all over 4 minus 3. Does everybody see that? And you might look at that and say, there is no way on this planet I would ever do that in Algebra 1. Right? But again, I'm crazy. All right, everybody okay with my crazy Algebra 1 way of doing it? All right, I don't know why I did that. It's just random. I talk way too much. So now, let's talk about this. So x minus 2, x plus 2, and that's a 3. Is log 3 a number? If you could type it in a calculator, it's a number, isn't it? Guess what we're going to do? I'm going to distribute. And so when I distribute this, this is going to give me x log 3 plus 2 log 3. And I guess I'll distribute that. It's going to give me x log 4 minus 5 log 4. Are we okay? Notice I'm doing the same thing here, right? Now what do we do? Oh, what did we do? Say that louder. I know the math makes it harder.
Get the x's on the same side.
Get the x's on the same side, right? Notice we had to subtract the 3x from both sides. What are we going to do here? Subtract what? I'm going to subtract x log 3 from both sides. So I'm going to subtract x log 3 minus x log 3, right? This cancels. And this is going to give me x log 4 minus x log 3, right? Okay, we got our x's on the right-hand side. What did we do with the number? Notice how we added the 5 times 4? What are we going to do here? Can we agree that's a number? So I'm going to add plus 5 log 4 plus 5 log 4. Did everybody see what I did? Yes? Mm-hmm. What's left on this side? 2 log 3 plus 5 log 4. Is everybody okay with that? If you look on the right-hand side, what's in common? Well, no, log 4. Yeah. This is x times log of 4. If I said x times the square root of 4, you wouldn't say x square root is in common. You would say x is in common because the square root's attached to the number, so the log's attached to this. So if I factor an x out, that's going to give me log 4 minus log 3. I get 2. Now, can we agree that this left-hand side's a number? Can we agree that this right-hand side is x times a number? What do you do to figure out how do you solve for x? Divide. Now, do you see that what we did here is exactly what we did here? Yes.
How come you were able to add the 5 log 4 to the other side?
It's a number. Notice I added that 5 times 4 to both sides?
So the bases don't have to match?
Well, they are. I mean, they're both 10. It doesn't. But everything we have is log 10.
Oh, okay.
Okay. And so our final answer is 2 log 3 plus 5 log 4 all over log 4 minus log 3. Did that make any sense? Well, more importantly, do you see what was important? Did you see that what we did here was exactly what I had over here? Now do you see why I didn't multiply out? Like I wanted you to see that 5 times 4 on this side so you recognize, oh, that's 5 times log 4 on this side. And you have to get used to this is thinking as a number.
So that's what our answer is.
This is what your answer is. And believe it or not, there is a question in Alex that's very similar to this. And this is the answer they want. They don't want the decimal. They actually want this. Which I think is, because honestly, when I give this problem on a test, this is what I want. I really don't care how well you can type it in the calculator. This is the answer that I want.
Is that for most of the stuff that we've done today? Like even math problems? Or it's like 58?
Some of them they want the decimal, some of them they want. Yeah. But there actually is a question that's very similar to this, that this is the answer they want. They don't want the decimal answer. All right. So